And that's equal to, well, the charge over per area. So I got this. So the only bit of charge enclosed is the charge that's sitting right here. Because I take my Gaussian surface, sort of clamp the two cups to my two virtual cups on the side of it, and I've enclosed a certain area and there's charge in there. So that charge is equal to that surface charge density times the area. So Q enclosed well, what's the area? Oh, I guess I need to get one other dimension here. I guess I'm using R for that distance. We'll make this distance from center to here, L. So what's the area that I've shaded in black over there? Yes. Pi L squared. So my electric flux is going to be equal to whatever my surface charge density is, pi L squared divided by epsilon sub 0. And I put it right here. So my electric, which equals my surface charge density times pi L squared divided by epsilon sub 0. Well, I know my electric flux density is equal to E dot A. So let's think about that. I've got my surfaces right here. So from a side view, I got my can looking like this, and that's the sheet. What's the direction of the area vector at this end? The direction of the area vector. Okay, out, and more specifically, which way out?
Away from the dog.
Is that away from the dog?
Well, perpendicular to the dog.
Okay. So perpendicular to the surface, just that way. What about the area vector on this side? Which way does the area vector here point?
Out perpendicular.
What about here?
Perpendicular.
Here?
Perpendicular, yeah.
Yeah. All right. So on the sides of it, my area vector is pointing out this way, parallel to the sheet, and this way it's pointing just away from the infinite plane. So I'm going to do this, and I'm going to break it up into three parts. I've got the electric field left dot area left plus the electric field right dot area right plus the electric field side dot area side. Basically covering the left, I guess left, right, and the barrel. And I know that's going to be equal to sigma epsilon pi L squared over epsilon naught. I think I misspoke there, I wrote it correctly though. Which way is the electric field going to point from this infinite sheet? it down. I got my infinite sheet here. I'm trying to figure out what is my electric field, let's say at this point right here, from this charge right here. So I'm just gonna look at a small little bit, the small little charge here, which way is the electric field? Assume it's positive. Whenever you're doing these, you assume positive, you work out the formula, if it happens to be negative, then wherever charge shows up or density shows up, you throw the negative in there. But assume it's positive, where's the electric, in which direction is the electric field pointing at this spot because of the charge that's sitting right here?
Maybe pointing like up. It's gonna be an angle.
Electric field points away from positive charge. So I've got a charge here, sorry, an electric field that's pointing it up and to the right. Now, if I got a point here, it's infinitely big, so I got another point over here. What's the direction of the electric field at this point? What's the direction of the sum of these two electric fields? Because the sheet is infinitely large, any of the way I've drawn it here, any of the vertical components are going to be canceled out by another electric field. The only thing that's going to remain is the electric field that's pointing away from this surface. So my electric field at this point is pointing this way, it's pointing this way, it's pointing this way, this way, that way, that way. My electric field is pointing away from the surface. So I've got my electric field, let's just take a look at this one first. My electric field is pointing that way, but my area is pointing that way. What is the dot product? Looking at this right here, E side dot A side. What's the dot product if my area is this way and the electric field is that way? Just shout it out in unison. 3, 2, 1. Yes, there we go. It sounded like a single voice. It was that crisp and clear. Dot products care about parallel, perpendicular dot product, or dot products of perpendicular vectors is 0. Well, we got rid of a third of our left-hand side, just like that. Here, on the left side, my electric field and my area vector are in the same direction. So this is just my electric field on the left side, which I'm just going to label as E, times my area on the left side. Well, my area on the left side is just pi L squared. On the right side, it's just the electric field, pi L squared again. There's no reason why the electric field a distance r away here and a distance r away here would be in a different magnitude. Because of symmetry. So I end up with 2e pi L squared is equal to sigma epsilon pi L squared over epsilon sub naught. So the magnitude of my electric field is, well, pi L squared cancels out very nicely. And I'm left with whatever my surface charge density is, divided by 2 epsilon sub naught. So using Gauss's law, exploiting the symmetries, we're able to now figure out, without calculus, the electric field coming off of a huge plane of surface. Questions to hear? I take a plane here and a plane here. I got 2 planes here. This is positively charged, that's negatively charged. Assume that these are infinitely large, or the distance between them is incredibly small compared to the size of them. my electric field from the positive charge. At this point, from just the this sheet here with positive charge, at this point right here, which way is that electric field going?
To the left.
What about over here? Which way is it going from the positive charges?
For the positive charge?
Because of the positive charge. Let's ignore this for right now. Which way is it going over here?
To the right.
Doesn't matter how far we are away, in our formula here, distance doesn't show up. How far you are away is irrelevant. Let's add a negative plate in here. Which way is the electric field here because of the negative plate?
It's gonna be going to the right.
Which way is it here because of the negative plate?
To the left.
Because the electric field goes away from positive towards negative. So, how far I am away from the place doesn't matter because the distance is gone. R never showed up. Out here, what's my total electric field?
Zero?
Out here, what's my electric field?
Zero.
Ooh, that was nice. In here, what's my electric field? They're going, the electric fields are going in the same direction. They're not going to cancel out like they did here and here. In the middle, they're going in the same direction. So what would the electric field be? All right, we have the formula for, if I had only a single plate, we know what the formula is. Let's assume that the surface charge density is the same on both. Just one's positive, one's negative.
Is it just gonna be 2 times that value right there?
Yeah. Or just sigma, so the electric field, sigma over epsilon sub naught. And then the direction is basically from the positive to the negative plate. Which I will crudely write like that. Yeah. Or probably better, why don't I establish, that's the positive direction, and so we can get away with this. I guess we'll make the magnitude different. That seems notationally correct. So we've got these two plates that are equal in magnitude and charge, even distributions, one's positive, one's negative. And we have no electric field outside it, but in between we have an electric field equal to this. Let's connect it with real life. That's a capacitor. Any capacitor you have ever seen inside electronics, they usually look like, they're not usually parallel plates in that sense. They're usually round. They look like a small little cylinder. But that's the principle behind the capacitor. It stores charge on the plates, and then all you need is some little connection, and then all the charge will actually go across. Or if you build up too much charge, that charge will just spark across. And there's some videos out there of people playing with that, where they build up to see at what point, how much charge can we put on this before it just sparks across. We get electrons jumping over, actually jumping this way. Why on earth, what's a practical application for I build up all this charge and then I want to release it all at once? So not just building up charge so it sparks, but I have some sort of switch here that when I connect it, we suddenly get this huge amount of charge flowing across it. What is a practical application for that?
Frankenstein.
What'd you say?
Making Frankenstein.
I assume you mean the monster.
Yes.
Possibly. I guess it depends. I guess they did do a jump start of the heart there, which, in more practical terms,
The defibrillator.
yes. Also, I've had one student who's claimed to actually have experienced this.
No, I was thinking jump starting the car.
I don't think that's the same thing. I think that's a gradual buildup and not the sudden dumping of charge. I'd have to look at that a little more carefully. Stun guns or tasers. I had a student who was former Marine, said he'd been tased once, peed all over himself. Like a brave man to say that in class. And also flashes for cameras. You get that flash, that's a buildup, you build up the charge, you do a connection, and then you get this huge amount of current. And matter of fact, you can make stun guns from the disposable cameras with flash in them, if they still sell those. And there are videos out there of people being stupid doing that, and then testing it on themselves. If you ever do that, if you ever take a disposable camera with a flash on it, make a stun gun out of it, and then zap yourself, please don't put that part on YouTube. Just stop it where you've made it, and don't show us your testament. Like, guy jumping into cactus. How many of you seen the guy jumping into cactus? Yep, at least one of you. I don't like laughing at pain, but I laughed at his pain because it was just stupid.
I said I was gonna do it, so I did it. I'm man of my word.
At this point, you'll be able to pick up hopefully a lot more off the videos. And the clock says it's almost time to go now. Nope, actually, this clock, Verizon says it's time to go. So don't forget to look in the lab section of Blackboard for the course, and you'll see the assignment that's due on Wednesday. And I'm trying to think if I actually made available the lab that we'll be doing on Wednesday, or next Thursday, in 2 days. Please have that printed out before you come to lab on Thursday. I'll make it available.
So the online lab is due Tuesday, or a week from now.
Yes.
And then the lab from last week is due Thursday.
Yes.
And then the lab we do Thursday is due next Thursday.
Yes.
And the next master set's due this Tuesday.
Pardon?
And the next master set's due this Tuesday. Chapter 19.
Yes, 18 is due today, 19 is due next Tuesday. Isn't 8 weeks fun?